Hi, this week we're going to be talking about composite functions, and specifically about inverse functions, and take a look at our first example of an inverse function, radical functions. We'll start off with a discussion of composite functions. Let's say we've got two simple functions, f and g, and we want to put them together in a very specific way. In fact, we want to kind of put one inside another. What do I mean by that? Just imagine we have our functions lined up, like, let's say we've got a function g, and we've got another function f. And we're going to do something very strange with them. We're going to put a certain input x into g, and of course when we do that, it's going to produce an output g of x. And we're going to take that g of x and put it in as the input to f. It's kind of strange, but if we did that, we would have f of g of x as the resulting output. And instead of thinking of this as two different functions and two different steps, instead we think of it as a single step. And we give a new name to this function that takes an input x and then produces an output f of g of x, and we call that function f of g. So that's what a composite function is. But the order actually matters, so we could also have it go the other way. We could say put our input into f first. Out of that will come f of x, of course, and then take that f of x and turn around and put it as the input into g, and we get g of f of x. And even though it looks very similar, these two things can be quite different. What we've got here is g of f. That's the name of our function. It takes an x and produces g of f of x. Let's take a look at some concrete examples. We're going to take a look at two different functions, and we're going to look at putting one inside the other in both possible orders, okay, to see what the difference is. So if I've got here for question number one, my f of x is a linear function, and my g of x is a radical function. It's got that square root in it. Let's say I want to talk about f of g, that function. What does it do to an input x? Well, it's like taking g of x and putting it in f. Well, what is g of x? It's 4 root x. And if I plug that into f, I take everywhere I see an x in my definition of f, and I replace it with 4 root x. So I'd have 3 times 4 root x plus 7. Oh, I can't help myself. I should just clean that up. All right, there we are in simplest terms. There's f of g of x. Okay? So for instance, if I wanted to calculate f of g of, I don't know, 1, I'd get 12 times root 1 plus 7, that'd be 19. Now, for the domain of f of g of x, if we take a look, we need that x needs to be greater than or equal to 0 because of our square root right here. So our domain is going to be all real numbers that are greater than or equal to 0. Now let's take a look at g of f. What if things are slightly different? This time I'm going to take the result of f of x and plug it into g. So we'd be taking g of 3x plus 7, which would be 4 times the square root of 3x plus 7. Now here our domain would be all real numbers that are greater than or equal to negative 7/3. So notice the domains are completely different. And in fact, these functions are completely different. If I try to plug 1 into g of f, well, I'd get the root of 3 plus 7, so the root of 10, and 4 times that. 4 times the root of 10. That's totally different than 19. Okay, so g of f and f of g are completely different functions. Let's take a look at another example. This next one is very strange. Okay, here we've got just a constant function as our f. So that means no matter what x you give it, it's going to very boringly give you an output of negative 4. Your g of x is a nice rational function. Okay, so let's construct, let's say f of g of x. So that would be f of g of x which is f of negative 5 over 3 minus 8x. Now, what does f do? Take a good look at it again. It essentially ignores the input. It doesn't really matter what the input is, it just gives an output of negative 4. So our f of g is going to do the same thing. So for instance, if I calculated f of g of, let's say, 1, I would get negative 4. Now the domain is a bit weird, because if we look at how f of g is defined, whatever our original x is, we need to be able to plug it in to g. And if we look at what g is, we see that an x value of 3/8 cannot go into g. So even though the output's always negative 4, the domain is all real numbers except 3/8. Very strange. Well, that's what it is. Now let's take a look at g of f. Well, g of f of x is g of f of x. F of x is always negative 4 regardless of what the value of x is. And if I plug negative 4 into g, we're going to get negative 5 over, over 35 there. And of course, we'll always put that in lowest terms, negative a seventh. So g of f of 1 would be, well, negative a seventh. So here again, we've got very different values. F of g is clearly different from g of f, because when you plug 1 into both those functions, you get different values. And the domain here, well, here we don't have the same problem. If I plug any x into f, okay, into our green function f here, I'm always going to get negative 4, so no problems there. And negative 4 goes fine into g. It's not going to cause any problems with our denominator there. Okay, so every real number can be plugged into my function g of f. Okay, so we see again the domains are quite different. The order matters a great deal. I'll let you try out number 3 for yourself here and figure out a few, maybe choose one x value and plug it into both and see what kind of function values you get for f of g and g of f. Figure out nice expressions for both of those two functions, composite functions, and also figure out the domain of both. In the next video, we'll talk about inverse functions, which play a very special role and will lead us to a discussion of many more functions in the next few weeks of the course. Thank you very much.